Hello, welcome, and thank you for joining us for today's webinar on basic UPS sizing. My name is Rob Rallo, and we're going to wait just another minute or two for a few more people to log in. So please be patient, give us just one more minute or two. Thank you. Okay, we're going to go ahead and get started. Anybody that comes late can always follow our webinars online. All of our webinars are recorded and are available online on our website within 24 hours after the webinar is over. Just a reminder, as always, please ask questions in the chat box, and we will try to respond to those at the end, most definitely, and sometimes on the way if it's pertinent to that. So with that said, we begin. My name is Rob Ralla. I'm a senior engineer with Sunwise Power and Battery. I have been in the solar business and the off-grid power business for over 25 years. And joining me today is Errol Rankin. As always, Errol's always in the background, but today Errol's going to do the online portion of our presentation today. Sunwise has over 20 years in the off-grid power solutions business, with manufacturing facilities on both the East and West Coast and installations all around the world. We offer a range of solutions, including standalone PV UPS systems, which we're going to talk about today, or battery backup systems, hybrid systems, and other systems as well. So pretty much any type of backup or off-grid power solution, we can help you with all of those. As I said, we got manufacturing facilities on both the East and West Coast, and we have sales and other facilities throughout the country. As I said, we can provide standalone power solutions, mobile power solutions, hybrid, cyclocharge, also known as CDC systems, backup or UPS systems, which we're going to talk about today. Custom module solutions. We can also provide just components if that's what you need, and we can also provide other services as well, engineering services, consultations, technical writing, training, troubleshooting, installation services, things like that. So we provide a whole range of products and solutions for off-grid and backup power systems. So with that being said, our today's topic is on basic UPS sizing, and I'm calling it basic because we have a little time at the end. We're going to get into some more of the advanced stuff. There are a few advanced applications we can do. We'll see if we have time for those or not. So right now we're just going to focus on the basic stuff. So with that being said, we're going to start with an intro. Then we're going to talk about the types of UPS systems. We're going to go into load calculations, battery derates, and this could be temperature, aging, and other. Then we're going to size the battery. Then we're going to size the battery and charger. Very important. You want to be careful with your recharge rates. You want to make certain that you recharge the battery not too quickly, but then you also want to make certain it's charged fast enough depending upon the application. Sometimes you're not worried about a 24-hour recharge, so sometimes you can go 1 or 2 days but for recharging. Sometimes you might need to recharge in less time than that depending upon your application. They're going to run through a few examples, and then we're going to go through the online sizing tool, and that's where Errol's going to take over. So let's go ahead and get started with an intro. Okay, so basically for a backup power system, we're going to have 3 main components. Okay, and again, there's going to be a slight difference between a backup power system and a UPS system. We're going to get into that in just a minute. So for that, you're going to have a primary power source, which could be, most people in general, it's going to be utility lines. However, you could also have other things. You could have a generator, you have a fuel cell, thermoelectric generator, also known as a TEG. So there are other types of primary power sources you can use. So sometimes those might be AC or DC related. In the case of a TEG or a fuel cell, it's DC related. In terms of the utility or generator, it's AC related. Okay, you can have a charging device. It's a device that converts the AC power to DC in the case of those AC sources. Obviously, if it's DC, it may have that built in or it may not. You may still need a charging device. And then, of course, the most important part is the batteries for energy storage. So basically, when the grid fails, then everything else just takes over. Or if your primary power source fails. Okay, as I said, there's a slight difference between a UPS and a battery backup. Okay, the UPS system, what's the difference here is the load draws power from the battery. So in other words, the load's always connected to the battery. Okay, and then when it's for that reason, then if the primary power goes out, the load doesn't know. There's no switching delay because the load's always running off the batteries. Now that could be an AC or DC load, so you might have an inverter in there or not. Okay, a battery backup usually uses an inverter charger or an inverter with a bypass switch in it, basically, and then it switches from the utility or the generator, whatever it is, over to the batteries, and there's going to be a slight switch delay in there, and we're going to talk about that a little bit more. Sometimes your loads can handle that switch delay, sometimes it cannot. Okay, so depending upon that, and also if the loads are really big, sometimes that makes more sense than to go to the UPS version, which is where you have to have like a massive battery charger to handle that AC load. So there's different reasons why you might want to go with either one. We're going to try to get in a little more detail here. Hopefully try to explain that better as we go through these slides. Okay, so let's talk about critical loads just a little bit. Okay, so the purpose of a battery backup is to sustain the loads after primary power failure. Okay, so you want to have sufficient time to allow for that primary power source to come back online before the equipment may go offline, basically before your batteries go dead. So that's always the hard part, is how much backup do you need? Do you need 15 minutes or 1 hour or 8 hours or 24 hours or 4 or 5 days? Okay, so that's a tough one to know. That means you have to understand your application situation. You have to know basically your utility or your power source, whatever it may be, and know how much time you need to get out there to help bring that main power online, whether it's a generator or a TEG or fuel cell. And if it's in terms of utilities, you need to know generally how long that's going to be down or how long until you can get another power source on there. A lot of these may have a backup generator, but it takes 15 minutes for that generator to power up and come back online. So you only need a 15-minute battery. So again, you have to, your application, know your primary power source and your backup power sources. Okay, you also need to know whether, in the case of, and this is the case of AC ones, DC ones, this is not applicable, but in the case of AC ones, whether you have a switching delay is acceptable or not. Most loads can handle a slight delay of about a cycle, which is 15 milliseconds. And if you remember our webinar on EE 101, we talked about hertz and cycles and things like that. We mentioned that a cycle is approximately 15 milliseconds. A lot of inverters will have a transfer time of right around 15 milliseconds, which is right around one cycle on a 60 hertz system. The thing is, some may have longer than that. Some may have switching times as long as 50 or 60 milliseconds, which might be too long at several cycles for your load equipment and cause it to go offline, defeating the whole point of having the UPS system. If your equipment goes offline and then comes back online, that wasn't a very good UPS. Other inverters may have things as fast as 4 milliseconds switch time, which is less than a cycle, which is incredibly quick. So it's important to know whether your system can handle switch delay or not. If it can't, you may want to consider going to a straight UPS and not having a inverter charger or an inverter transfer switch in it if it can handle that switch delay, or find yourself an inverter with a transfer switch that is fast enough to be able to handle your load. And again, it depends on your load and what it can handle. As I said before, I think in most cases, most loads can handle a switch delay of around 15 milliseconds. Usually usually the loads will have capacitors, inductors, and some type of energy storage device in it that allows it to handle a slight hiccup, essentially, in the power without it being an issue. Okay, the other thing about the reason we put UPS or backup systems in critical loads is because when it goes down, it costs money. I know in the oil and gas industry, sometimes if the well is down, it costs them $1,000 an hour. That's a lot of money. So all of a sudden, the UPS system starts to look cheap. So basically, if you're down for, if a UPS system could save you from being down for 5 hours, save you $5,000, and the UPS system costs less than $5,000, I think it's pretty much a no-brainer. It seems to make sense at that point. So again, although these things can be expensive, if your downtime costs more than that, then ends up becoming a pretty cheap solution. Some applications where they use it, I mentioned oil and gas already. Telecom, it's another one. You don't want your cell phones to go offline. SCADA, security purposes. I mean, that's a big one because basically it's the whole point is for someone wants to steal or break into stuff, they're going to go ahead and cut power. So obviously it's very important to have that. Utility water can be another big one. Monitoring and agriculture. Okay, so uninterruptible power supplies, UPS, basically a backup power supply. It supplies power to the load when the input power source fails. Okay, and you can have multiple input sources. As I mentioned before, you might have a utility, then you might have a backup battery that takes over for a certain amount of time before you might have a backup generator that kicks in. Like I said, sometimes the generators might take as much as 15 minutes to come online and to start up and warm up before they come online. So you might have to have another source of uh, energy in there in the meantime as a battery. So that's a possibility as well. And again, they can be installed indoors or outdoors. If it's outdoors, you got to make certain that the equipment, and to be honest, most of our applications actually are outdoors. You need to make certain that you have the appropriate environmental stuff in there for that. The temperature compensations, the batteries in appropriate enclosure, and things like that. So you need to make certain your system is designed for outdoor use. Okay, again, the loads can be AC or DC. AC loads will require an inverter, obviously, because the batteries are DC based. DC loads may need a low voltage disconnect, and that's if you want to prevent your batteries from getting to an extreme low point that may actually cause them to be damaged and sulfate. Okay, so low voltage disconnect may be useful there. Also, you need to verify your DC loads can operate within the battery voltage range. A lot of people forget that. They're going, oh, well, I've got a power supply in there, or whatever it is, and plus or minus 5% is fine. But when you're operating with a battery directly, then you got to remember the battery voltage range is minus 10 to plus 20% of the nominal voltage. So in other words, a 12-volt battery may range from like 10.5 volts up to 14.5 or 15 volts. Okay, and if your load can't handle that, then you may need to put in a DC-DC converter or some other type of load conditioning equipment to prevent it from seeing voltages outside that range. And again, that people always say, well, can we change that battery voltage range? No, you can't. That range is needed for the battery to operate properly, especially on the plus 20%. If that battery is not properly charged, then it's going to get damaged and it's not going to do you any good at all. So it's very important to understand that range is not negotiable, and that you'd have to put in power conditioning equipment if the load cannot tolerate that. Okay, we mentioned UPSs a little bit before, different types. We have the TEG, which is thermal electric generator. We have a fuel cell. There's DC generators and other ones where the charging source is DC. And with these DC sources, they may have chargers built in them, they may not. So you might be able to connect these directly to the battery and then connect the load directly to the battery. And in some cases, you may have to have a charge device in between and or a load conditioning, like a DC-DC converter in between. So we're going to show a few examples of that in a minute. Okay, here we go. So again, you've got your DC charge source. So in this case, this is something crude. A lot of your thermoelectric generators, especially the old ones, are just crude. They pump out, something like for a 12-volt system, like 30 volts. There's no temperature compensation. There's nothing to it. It just pumps out a steady voltage and current pretty much. So you need to put a controller in there of some form to properly charge the batteries. In this case, a lot of our charge controllers also have load controllers in them that basically are just a low voltage disconnect for the DC load. Now, again, this is a situation where there's no load regulation, so it's seeing the full nominal battery voltage, full battery voltage, which is minus 10% to 20% of the nominal voltage. Okay, so here's one with an AC load. So basically, you're doing something similar. You're taking the DC source, running it through a charge controller, and then you've got that going in your battery. But in this case, you've got that coming out and going through an inverter to the AC load. Okay, here's an example of one, which is basically that requires a DC-DC converter because the load can't handle that minus 10 to plus 20%. So in this case, the DC-DC converter usually can do a load regulation of plus or minus 1% of the nominal voltage. So if it's a 24-volt system, it'll be like 23.5 to like 24.5 volts, which is, or even less than that actually, which is what the load might want. Okay, and it's kind of the same thing here. You get your DC source, you get your charge/load controller, which has got your LVD in it, you got your battery, and you've got, of course, as I mentioned, DC converter going to your load. Here's one where you can have the charge control built into it. A lot of the new fuel cells, because they're already pretty sophisticated, are sophisticated enough to actually have the charger built in, including a temperature compensation probe in it. They have a remote temp probe. for that can hook up to the battery. So so again, that just goes directly to the battery, as I mentioned. Now, you may or may not want to have a load control in the output. Now, load controller is basically just the low voltage disconnect that I mentioned before, and then that can go directly to your DC load. Same type of thing, except for instead of having a DC-DC converter, you've got an inverter, or excuse me, instead of a load controller, you get your inverter. Now, a lot of the inverters nowadays, in the old days, didn't have that, but the newer ones have low voltage disconnect built in. So a lot of times you'll see us not add the LVD as it's already built into the inverter, which I'm assuming in this case. And then that goes to your AC load. And here's a version with a DC-DC converter. In this case, we do have the load controller in it because most DC-DC converters do not have a low voltage disconnect built in. So we've added that in front of the DC-DC in this diagram, in this example. So now let's talk a little bit about the AC UPS ones. Okay, the AC source can either be utility, AC generator, or other. And you'll see that they're pretty much very similar. Again, you've got your AC source instead of your DC source. You got your battery charger, which is going to convert your AC or DC. Then you've got your battery. Then you've got your LVD again, low voltage disconnect load controller, and then there's your DC load. Again, notice that this is a load that can handle the minus 10% to 20% of the nominal battery voltage. Okay, and here's an AC load example, pretty much the same thing, other than we've got the inverter added in there on the output to the AC load. Okay, and we've got a version now that has a DC converter in there as the DC load needs to be regulated. So, and again, same thing we've already seen before. You've got your battery going to your load controller, which is your LVD, and then that goes to your converter and then out to your battery. Actually, that's your load. Okay, and this is a slight difference with the AC backup system versus the UPS. You'll notice here that the AC source goes in the inverter charger and then goes out to the AC load. Now, there's a transfer switch built in, so basically that's just passed straight through. So the AC load can see the AC source directly when it is there, and then at the same time, the inverter charger can charge the battery up. Now, when that AC source goes down, then the inverter charger will flip that transfer switch and start inverting. And again, there's usually a slight delay there between both the switch and converting to invert mode, and that can take anywhere from, depending upon the inverter charging, there from like 4 milliseconds up to 50 milliseconds or so. And then that will power. Then at that point, the battery will power the AC load through that inverter charger. So here's an example with an inverter with a transfer switch. So instead of the inverter being able to charge the battery, it's the same type of thing other than it can't charge the battery. So if you notice in the previous slide, there's arrows going both ways. So you can see the current from the battery going into the inverter when it's inverting to the AC load. And you'll see the arrow going as a charger into the battery when it's in charge mode. And that's when the AC is available. In this case, you'll notice that the current can only flow from the battery in the inverter when it's in invert mode. So it has to get charged to a separate battery charger. And that's okay too. I mean, there's nothing wrong with that application. Just giving you other options here of what can be done and what you might see. Keeping in mind, you still have these transfer switch issues with that inverter. Okay, same as the inverter charger. Nothing changed there because it still has a transfer switch in it. So what I want to summarize about this all is that there are many configurations, many options, multiple input sources. Again, I've shown all of these with just one, but you could have multiples on some of these. You can have some AC, you can even have some DC. I've worked on a couple recently. We actually have AC and DC sources going into the battery. So to try to summarize that all up, if you are not certain, please feel free to contact us at Sunwise. We'll be happy to help you figure out which configuration works best for your application, because there are a lot of options here, and trying to figure out the one that might work best for you may not be quite so simple to figure out. So if you're not certain, please feel free to call us. We've been doing this for many years, so we'd be happy to help you. So that being said, just to let you know, with regards to these systems, there are a couple of industry standards that can be referenced. IEEE 946 is the recommended practice for design of DC power systems for stationary applications. And IEEE 485 is the practice for sizing lead acid batteries for stationary applications. And basically, a stationary application, in this case, is a UPS application. Okay, so let's go through the sizing methodology now. So first, we're going to calculate the load in amp hours, and just to let you know, it's the same process we have to go through for a standalone PV system as well. You always got to know your load. So first, we have to calculate the load in amp hours. Then we're going to calculate the battery. And then we're going to calculate the desired charge current, or basically select the correct battery charger so we have the correct recharge rate. And that's very important. You do not want to charge your batteries too quickly. And in some applications, you may not want to take too long to recharge your battery. And we'll get into that in more detail when we get into the battery recharge part of this. Okay, so let's go to load calculations. So if you know your load in amps, that's great. Then you're just going to multiply that by your backup time and you get your amp hours. If you know your load in watts, you're going to divide by the nominal battery voltage and then multiply that by your backup time. That's going to give you your amp hours. Now, I want to note here that you need to figure out your backup time. Only you know what that needs to be for your application. Okay, again, it could be 15 minutes, it could be 1 hour, it could be 8 hours, it could be 24 hours, or even more. It could be 72 hours. So you need to best determine that. If you need help, we're happy to help you here at Sunwise to try to figure out what would be best for your application. But keep that in mind that that backup time is what is determined based upon your needs for your system and your application. So let's just, for more information on understanding your loads, we have a tech note on that. The hyperlink is right there, or it's in our handouts, by the way. So there's a handout for that also. So just to run through a couple of examples. Let's look at a 6 amp continuous load for 24 at 24 volts for 8 hours. So the 6 times 8 is 48, and that's again at 24 volts. Then we've got a 15 watt continuous load at 12 volts for 24 hours. So the 15 watts divided by the 12 volts gives us 24 hours. Times 24 hours gives us 30 amp hours at 12 volts. So pretty straightforward calculations there. Okay, now a couple of things to keep in mind with these are loads at non-system voltage, which again would be AC loads or loads that require a DC-DC converter. You need to make certain that you include the inefficiencies there, the losses. So and a lot of inverters are around 90% efficient, so you would need to add an additional 10% for those losses. And converters can range anywhere from 80 to 90% efficient, so you may need to add an additional 10 to 20% there to calculate to add to for those losses. Okay, in your calculations. Okay, intermittent load should be averaged. That's another common one. You might have an intermittent load there. You might have radio with a transmit and a standby. You may have a pump that comes on and off or something like that for water things, or for oil and gas. So if you have intermittent load, that should be averaged, and that average should be over your backup time, over the duration that you expect this to operate. Okay, you may want to include future expansion, especially in telecom, where you may have you may have more activity on that cell tower or something like that. Okay, you may also want to add in a little extra fudge factor for uncertainty, as I mentioned before, on run times, again, for radios, pumps, things like that. So if you've got intermittent loads in there, you're not 100% positive on the duty cycle, add a little extra fudge factor for that, just to be on the safe side. And also consider inrush currents for the AC loads. It's not important for actually sizing the UPS system, but it is important for sizing your inverter. Okay, so if you're going to have an inverter in there, it needs to be able to handle the inrush current for your AC loads. There's especially important when it comes to pumps and motors and stuff like that. So just some additional considerations there for the load calcs. Okay, so we're going to move on now to battery derates before we get to the battery calculations. Most common are temperature and age. Temperature is a real common one. Okay. But you're going to deduct that derating from the battery capacity. So whatever your battery capacity is, you're going to subtract that derate from it. We're going to do a couple examples of that. As I mentioned, the two common ones are temperature and age. A common age derate is 20%. That comes out of the telecom industry, because once the battery has been reduced to 20%, 80% of its capacity because age, they consider the battery failed and they throw it out and put a new one in. And the solar industry will let those go a lot further than that. But the telecom industry was very big on having, especially in UPS applications, having batteries that once they were at 80% of their capacity were no longer functional, and would remove those and put a new set in. So that's why on UPS applications, a common age derate is 20%. For temperature derate, you have to understand the temperature operating again. And again, if you're in an indoor application, temperature derate is not needed. But if you're in an outdoor application, you absolutely need to include a temperature derate in there. And I'm going to show you a curve for that. But I would refer to the battery manufacturer for your derate curves. Most of them are right there on the battery spec sheets. If not, then I would contact your manufacturer for that. But again, most of your derate curves are right on the spec sheet. I'm going to show you an example of that in just a second. Yep. Oh, I just want to mention high temperature also has an effect, but that just affects the life of the battery. It doesn't actually affect the capacity. So I just wanted to point that out, that sometimes people think that people mention the high temperature. High temperature doesn't affect capacity, just the cycle life of the battery itself. Okay, so again, this is only cold temperatures affect the capacity. And here's an example of a curve. This one is from MK Battery, actually, for their HE batteries. And you'll notice that right around freezing, right around here, right around 32, you'll notice that the battery capacity has derated to approximately 83, 83%, something like that. So it's not uncommon for people to use, again, an 80% capacity for temperature derate again. Somewhere around here. So again, if you want to go a little conservative, go with 80, that's fine. But all that's pretty common is use 80% for a temperature derate of right around freezing. So it's a common one to use as well. Okay, so again, let's say you got as an example here, let's say you got a 100 amp hour battery at 25C, which is normal room temperature. And let's say again, it's at 0C, which is freezing. And we're going to use an age derate of 20%. Again, that's pretty standard. So so from the okay, so the temperature derate is approximately 18%. Like I said, it's about 82% of the capacity still there. So that means it's going to derate by about 18. So you're going to have 100 amp hours times 0.08 for the age derate times 0.82 for the temperature derate, and it's going to give you a new capacity of 65.6 amp hours. Notice it's quite a bit less. That's quite a bit smaller than your 100 amp hours. Okay, but that's the capacity you would use in your sizing. That would be the 65.6. Okay. So just keep that in mind. So all of a sudden, a 100 amp hour battery you were going to try to use just as it was may not necessarily give you what you need. And this is very important in a UPS application. If you expect that battery to give you, 8 hours of backup, you want 8 hours of backup. You want it in all conditions. And if that battery's been sitting there for 5 years, it may not be at 100% capacity anymore. It may only be at 80% of the capacity. And again, if it's cold out, it's not going to be 100% capacity either. So these derates may seem extreme, but if you want, again, this is a critical application. You want this UPS to work. You want your load to be up, and you want it to operate, 5 years from now in a cold temperature. Then these are the derates that you need to take into account for it to be there when you need it to be there. Okay. I also want to point out something else, and that's that the capacity changes with the discharge rate. And again, I'll show you a capacity rate chart in just a minute. But so basically, the battery will have a greater capacity at a 100-hour discharge than a 20-hour discharge. So you got to keep that in mind. And most UPS applications, again, might be at a 1-hour rate or a 24-hour rate, or even a 15-minute rate. And again, those are going to give you different capacities than, say, a 100-hour rate for, say, a solar application. So again, that 100-hour rate for solar is going to give you way more capacity than a 20-hour rate for a UPS application. So it's important to make certain that you use the correct capacity based upon your backup time. And I'll go through that in a couple of examples here as well, so you get the idea on that one. But it's important to understand that. Also, generally, we're going to go to a depth of discharge of 80%. In a UPS application, you usually don't cycle the 50, you usually cycle to 80%. You want to try to get the most you can out of the battery. We will not go to 100% though, typically, because you get 100%, you may damage the battery. Now, in some applications, that may be okay. You may want to, risk damaging the battery to keep that load up, whatever it is, rather than have it fail. So in some cases, you may want that, but a lot of the cases, you want to go ahead and only go to 80%. So keep that in mind as well, that your average depth of discharge is going to usually be about 80%. On most of these, you typically do not go beyond there. So saying, here's an example of that. Again, if you go with your 100 amp hour battery, which is basically your HE27 here. Again, this is the Deka HE battery chart. you'll notice that, say, the 1 hour rate, 60 minutes, it's only got a capacity of 57 amp hours. Okay. At the 8 hour rate, that same battery now, instead of being 57, is 78. And then at the 24 hour rate, it's up to 88. And at the 100 hour rate, it's basically 100 amp hours. It's 99 amp hours. What you'll notice, though, is that as you extend out there, you'll notice that there's a huge jump from the 57 amp hours at the 1 hour rate to, say, the 78 amp hours, the 8 hour rate. But you'll notice that the jump from there isn't quite as much. It's kind of it's not really a linear chart. It's more exponential. So the further out the discharge rate, at some point you really don't get any extra capacity out of it. You'll notice that even between the 40-hour rate and 100-hour rate, there's very little difference. There's a difference of only about a little over 4 to 5 amp hours. Not much difference there. But do keep that in mind if you're working in the fast discharge area, that your battery's going to have much less capacity than, say, a longer discharge rate. So you need to look at these charts and use these when you're sizing your batteries for your UPS application. And again, we'll go into this in an example in just a minute. So as I mentioned before, the difference between the 20-hour and the 100-hour rate there. Okay, so let's go into the battery calculations. So you're going to take the load amp hours that we calculated before. You can divide that by your battery depth of discharge. And again, normally it's going to be about 80%. Then you're going to multiply that by whatever derates you got. That's going to give you your required capacity. So if we go back to the same examples we used before, with example 1, we had that 6 amp load that was continuous at 24 volts for 8 hours. So it gave us a load of 48 amp hours. Okay, so we take the 48 amp hours, we divide that by 80% depth of discharge. Okay, and then we're going to multiply that by 1 plus the temperature derate. Okay, and that's going to give us 72 amp hours. So again, we're just going to go ahead and use as I mentioned before, a temperature derate. We're going to assume the battery has only got 80% capacity. We're going to say it's going to be cold. It's going to be around 0 degrees or something like that. So we're going to go ahead and just do that. So basically, we're going to take that and multiply by 1.1 to take into account that derate. It's going to give us the 72 amp hours. Okay, now again, we need to find that we need a battery that can do 72 amp hours. And again, that's at the 8-hour rate. So if we go back to the HE27 battery I mentioned before, it's rated 78.4 amp hours at an 8-hour rate. So that'd be perfect because we only need 72. So it's going to give us a few extra amp hours in there. So that would be the battery we choose. That would be what we want because of that. Okay. Now again, remember this battery is only rated 78 amp hours at the 8-hour rate. It's not rated at 100. Okay. Oops. So in the second example, we had a 15 watts continuous, and we had that at 12 volts, and that was for 24 hours. So it gave us a load of 30 amp hours. Okay. In this case, we're only going to go to a 50% discharge. For whatever reason, maybe we're going to cycle more frequently or something like that. We don't want to discharge as much. So we're going to divide that 30 amp hours by the 50%. Then we're going to multiply that by a 40% derate, extreme temperature. I've seen that before. I mean, actually, I think the East Coast is seeing that right now, to be honest, extreme temperatures, -10 in New York and stuff like that last week. So that 40%, although it may seem outrageous right now, when you're thinking about it, may not actually be given what's happened last week on the East Coast. So anyway, you multiply that all out, and it's going to give you a 84 amp hour required. So you need a requirement of 84 amp hours. Notice you can use the same HE27 battery. Even though it was only rated 78 amp hours, the 8-hour rate, we're now at a 24-hour rate. So we can use that because it's rated 88 amp hours at 24 hours. So just keep that in mind. You got to check those rates and make certain you're using that when you're selecting your battery capacity. Okay. So let's get into battery recharge time. A couple of important notes here. It should be no quicker than 3 hours. And that is because if you recharge your battery faster than 3 hours, you're going to damage your battery. Lead acid, especially the valve-regulated acid batteries, are not designed to be recharged quickly. Now, there are some newer technologies out there that can be recharged in 1 hour or less. Lithium-ion, there are some new nanocarbon technologies in lead acid batteries. So there's newer ones out there that can allow you to recharge faster. I will say this though, in most cases, there seems to be no reason to recharge your battery in less than 3 hours, to be honest. So I don't know that you need to spend the money for those other technologies. Lithium-ion can be quite expensive. It can be 4 to 5 times the price of lead-acid batteries. So I don't know that you need to spend the money for that. So just keep that in mind that most valve-regulated lead-acid batteries cannot be recharged. It should not be recharged faster than 3 hours. A typical recharge rate is somewhere in the 8 to 24-hour range. But it could be longer. I mean, there's no reason why it can't take 48 hours if you need that, or even longer than that. So if unless you expect to have an immediate outage again, there's no reason why it can't take even 2, 3, 4 days to recharge if you need to. But typically, a recharge time of 8 to 24 hours is pretty standard. Also, remember, don't forget to subtract the load from the charger output. That's an important thing. In these UPS systems, you got to support the load while recharging the battery. So you need to subtract that out of the charger, and then the remaining is what you can use to recharge the battery. Also, you don't want to you also want to check the recharge rate without the load. So just in case something happened, you have an intermittent load, a variable load, or that somebody turned the load off, or who knows what. For whatever reason, you want to make certain that that recharge rate isn't too fast to damage the battery when the load is not there or turned off. So you need to be very careful with that and double check that as well. So the formula is pretty simple then. You just take your battery capacity, the discharge capacity, then you divide that by the charger output minus the load. And that'll give you your estimated recharge time in hours. Okay, so if we go back to that example one, the same we've been using, okay, and we remember we came up with that 78 amp hour battery. Okay, so if we take that battery, again, we're only discharging the 80%, so we're going to multiply it by that, which means we only need to put 62.7 amp hours back in the battery. Okay, and so let's go ahead and use a 15 amp charger. So we're going to take the 15 amp charger minus 6 amps. It's going to give you 9 amps left. So the 62.7 divided by 9 is going to give you an approximately 7-hour recharge rate, which is pretty good. That's pretty good recharge rate. Go to example 2. Remember we had that 80 amp hour battery, but we're only discharging the 50%. So we really only need to worry about recharging it back to 44 amp hours. So if we try to use a 15 amp charger on that, and we have a smaller load here, our load's only 1.25 amps, that leaves almost 14 amps to recharge this battery. That's going to be 3.2 hours. That's pretty quick. It's almost faster than 3-hour recharge. So although you can do it, you may not necessarily want to use a 15 amp charger on that one. It might be a little too quick. So you could go to a 10 amp, or in this case, I looked at a 5 amp as another option, and that ended up taking about 12 hours, which might be pretty good too. So I mean, any one of those would be acceptable, but I probably personally go to either a 10 or a 5 amp on that one. I think the 3-hour recharge might be a little bit faster than you need on that one. Again, it's still okay. You're not going to damage it recharging it that quickly. It's not less than 3 hours, but it is kind of close to that point. So you may want to just consider a slightly slower recharge rate there. Okay, so at this point, I am going to turn it over to Errol, who's going to talk about our online sizing tool. Errol, you still there? I'll go ahead and get started, Errol, and you can just chime on in when you get a second. Okay, so we have, keeping in mind that Sunwise can provide fully customizable battery backup UPS solutions for you. Okay, we have many already standard packages available for you. We call it our Power Online series. Okay, and you can go to the hyperlink there, and you can learn more about those. We can provide those. Those are customizable. Sorry, customizable ones are the Power Online. We also have our already kitted, ready to go standard ones that are also available. And again, our website has more information on both of those options for you. Okay. The neat thing about the kitted ones are we can get those out the door faster because we're using standard parts, so we can usually ship those out in a matter of days or even a week or two sometimes, whereas the customizable ones may take 3 to 4 weeks or more depending upon the customization needed for those. Okay, I mentioned that we have it on. Oh, Errol's back. Okay, want to jump in here, Errol?
Yeah, sorry about that. I got kicked out of my own webinar. All right, so yeah, as Rob was mentioning, these links will take you to both the landing page as well as the design tool that we're going to cover for these POR kitted battery backup systems. All right. So the online design tool and our standard POR series systems cover AC input sources. So from the graphics that we reviewed earlier on in this presentation, the primary power source for all of these systems is going to be AC. And the load side of things are going to be for DC loads at nominal 12 and 24 volt voltages. Okay, so our solutions for this range of standard systems includes both ground-mounted and pole-mounted enclosures, all of which are outdoor rated and include powder coating. And these are meant to be standard solutions for a broad range of core DC UPS applications. So that includes a 3-day autonomy period for daily loads that range between 25 and 850 amp hours. And so we'll go over that in a little bit more detail, but that provides from a high level the range of applications these are designed to meet the needs for. So if you'll see here, we have a temperature profile map for average winter temperatures throughout the contiguous United States. We have broken up our tool into 3 easy-to-use categories. 3 easy-to-use temperature profiles, let's call it that. On the lowest end, for the most extreme case, we basically have negative 15 degrees Celsius. And that corresponds with average temperatures in the most northern latitudes. Similarly, at 0 degrees C, you can see that covers most of the mid portions of the country. And then as we move towards the south in areas like Texas and Florida, we move towards an average low temperature close to ambient or 25 degrees Celsius. So just by using those 3 temperature designations, you can get relatively accurate information about your system just by choosing the appropriately conservative value. All right, so this shows an example of the load lookup tables that are available for our POR data sheets and really explains a lot of the math and the rules behind the online sizing tool that we're going to go over. So if we just quickly review a few pieces of key information, you'll see that the lookup table is broken up into 3 different sections for the temperature profiles. At the left, in blue, you have the lookup tables for temperatures at negative 15 degrees C. In the middle in red, you have for 0 degrees C. And on the right in green, you have temperature profiles for 25 degrees C. Now, within each one of those, we similarly have 3 columns for the 1-day backup, 3-day backup, and 5-day backup periods. So that's 24 hours, 72 hours, and 5 days. Now, if we go through the rows, you can see that our charging source, that's the amount of amps that's delivered to the batteries, ranges from 4 amps to 80 amps continuous charging. We also have the dimensions of the enclosure. Since this UPS system is completely contained within the form factor of the enclosure, that gives you an idea of the size and the footprint for all of these. And then using the lookup tables based on your site's temperature and your application's load requirement, you can choose a standard system that will meet needs anywhere from a low-end range of 11 amp hours per day for a 5-day backup in a negative 15 degree zone, up to a load limit of over 1,200 amp hours for a 1-day backup in an ambient temperature zone. Okay, and so we've developed a tool, which is what we're going to go over, that makes this a lot easier. But of course, if you're ever out in the field or just want to use a simple lookup table, it's as easy as doing that. Okay. So if we go to the tool, which we referenced on that first slide, or in the slide a few moments ago, if you go to our website, it's under the Build a System dropdown, the POR design tool. So this tool has 2 major components. The first component is going to be entering our project information. Those are the primary column headers that we just went over on the last tab. So on the left, you simply enter your project temperature input, -15, 0, or 25 degrees C. And on the right, you enter your required battery autonomy requirement. Now, if you are in a zone that's in between any of these values, simply choose the most conservative case to get a budgetary number on a system that we know is going to work for your application. And then you can reach out to a sales executive and drill in, if necessary, to a more specific solution if that becomes necessary. Okay. So the second major step, once we enter the temperature information and the autonomy information, is to simply enter our loads. Now that's the other major component to this. Now we have two ways that we can enter your load information into this tool. If you already know your load information, you've already done those calculations, we have a simple direct input option. You can simply enter your loads in amp hours per day numerically. Similarly, we have an online load calculator. If anybody has used our solar design tool, our PRE design tool, this features the same load calculator capabilities. So that also will allow you to configure up to 3 discrete loads at a variety of voltage, runtime, and load unit options. So you can put in amps, watts, non-standard voltages, include conversion efficiencies, and all sorts of cool things. Okay, and then the final step, of course, is actually defining your battery bank voltage. All right. So in the load information on the tool, you can see there's two basic options. On the load input buttons, you either enter your information by choosing the I know my loads, total loads tab, or you can choose the use the load calculator tab and use that. Okay, next slide. Now, I want to note for the battery bank voltage, this is a design decision. This is something that the customer is going to have to make a choice on. Really, at the root of the issue, we recommend that the battery bank voltage be chosen based on your largest load voltage. So this is only really an issue or applicable if you have loads at multiple voltages. If you do, take the voltage that has the largest power consumption and use that as your wired battery bank voltage so as to minimize energy losses from any power conversion equipment. Okay. So option A is that you know your total loads. You'll see below there's a input box to enter your total average daily loads. That's just a numerical value of your amp hours per day at the specific voltage in question, the battery voltage. So that'll either be at 12 volts or 24 volts DC. Okay. Option B is to use the load calculator. As you'll see in the bottom there, there is a button for choosing the total number of discrete loads. I encourage everybody to use that tool if they haven't already. It's really great and handy to do a lot of math conversion if you haven't already done all that work on a spreadsheet, for instance. Again, you can control things like runtime. You could have one device that's a radio that runs 8 hours a day, another device light that runs 24 hours a day. They can be at disparate voltages. You can control all of that, and it'll sum everything together into a total daily load in amp hours per day that can then be fed into the tool logic to give you the system that you need for your application. All right, next slide. So once you've entered correct information for your total loads, your temperature information, and your autonomy requirements, and you've selected a nominal battery bank voltage, then you can hit the confirm button, hit the submit, and it'll basically take you to our web store for a specific system that can be ordered in a single part number and that will meet all the requirements of a UPS outdoor rated system with the loads, temperature profile, and autonomy requirements that you've entered. So that's a simple way that we've tried to allow our customers to get budgetary numbers and or exact project system quotes online easily in just a couple of minutes, 24 hours a day. Again, this can be really helpful in determining project viability, early budgetary considerations to determine whether or not you want to move forward with a more specific quote that a sales executive from Sunwise may be able to help you out with. This doesn't necessarily mean it's the absolutely best lowest cost solution, but it should get you more than 90 or 95% of the way there in just a couple of minutes. All right, and one thing I do want to add is there are bounds to this tool, of course. As I mentioned, there is a limit depending on the temperature and the autonomy of 12 or more 100 amp hours per day. Now, if you try to run a daily load requirement of 1200 amp hours per day, but you want 5 days autonomy in a negative 15 degrees Celsius zone, we don't have a standard solution that's that large. So it'll indicate to you that the system request or the design request is outside of the bounds of our standard systems. It will redirect you to our general system sizing form on our website, where you can submit all your project information to be quoted by one of our fully customizable Power Online systems. And of course, we can meet nearly any battery backup solution using that product line. And so if there's a standard solution that doesn't exist, use our system sizing form and we'll quote you a fully customizable solution that can meet any needs. All right, Rob, next slide. Rob, do you want me to hand this back over to you so you can talk briefly about this advanced sizing example? We'll give Rob a couple minutes here. We're trading back and forth.
Yeah, Errol, before we get into this, before we get in this application, I wonder if you want to answer a couple of questions first. We may or may not have time for this. We've only got about 8 minutes left. So I wanted to see if we wanted to get in that first. The questions first. I know one of the common things people are going to ask is, and I'd be surprised if somebody actually asked the question already, is can I add solar to my UPS system? That's a common one.
I did see that question.
You did?
Yeah, I did see that.
Okay.
Well, there's a question in here from Chris, actually. I was presenting and I had the chat or the questions box minimized in the background. Yeah, it's a great question. I don't have a simple boilerplate answer to this, but I do have a couple valuable pieces of information. The first piece of information is that specifically for these POR standard system lines, now we can do customizable POR systems, but when I refer to standard POR systems, that is the list of part numbers that are listed on our POR data sheet and for which the POR design tool is integrated around. That's about 15 to 18, I think, SKUs. So that's our standard systems. We can do customizable POR systems, and for those, a solar input option would be totally fine. Now, for our standard systems, whether or not solar could be inputted depends on the amount of free space that we have on the back plates and the side plates for each one of our enclosures. And that will vary slightly from system to system. So there may be some of these that have sufficient free backspace to add an extra charging source in there to do the solar input, and it wouldn't be an issue. There may be other ones where we wouldn't have that space. So I think the answer to your question with regards to the standard line is that it's going to change on a system by system basis. In terms of if you reach out to a sales executive and say, I want this standard part number, but I want solar inputted, we can definitely do that. It just needs to be requested.
Well, and the problem I always have with adding solar to your UPS system is why do you want to? What are you trying to achieve? Because the why is the most important here. If you're trying to reduce dependency on utility, then you're more into a solar utility hybrid. We've had a couple of those lately where they're looking to just reduce their electric bill or trying to be more green and whatever it is. That's different than if you're trying to increase your reliability. If you're trying to increase your reliability, then you've got a problem because now you have to try to calculate how much solar you're going to have, when you're going to have it, and is it going to be available to you when you need it. So that gets a lot trickier. And in the end, you almost end up sizing it, again, back to a hybrid type solution or as a standalone system, one or the other. So again, the big thing about adding solar is how much you're going to add and why. And again, the big question is why. Why are you adding it? Because depending upon why you're adding it is how much you might want to add and what it's going to actually do for you. In a lot of cases, it may do absolutely nothing. If you may just put 1 or 2 solar modules up there, it may do absolutely nothing for you whatsoever. But if you put a couple more up there and/or increase the battery size, because you also need to have some storage, then it may do something. So again, I think that the big answer, my perspective, is can you add solar to it? Is yes, you can, but the question is why would you want to? What are you trying to achieve? And then based upon that why is to how much you may actually want to add. Again, the other thing is when you do that, also double check your recharge rates. It gets back to, don't try to charge your batteries too quick again. So you got to go back and go through those calculations as well. So I actually had a slide on that. I was going to get to that one at the end, but I figured someone was going to ask that, so I want to make certain we covered that before we went on to some other topics. Errol, any other questions in there you see that we probably should answer before we move on to
no other major questions right now. I think we got a couple minutes. We can hit this last topic.
Okay, so let's do a little bit of advanced. Let's do an advanced example real fast. One of the common applications we're seeing frequently right now is light pole applications. People are trying to install Wi-Fi and other equipment on light poles because it's easy to do. These things don't require a lot of power. But the issue is that you only get power on the light pole when the light is on. So that means you only have it for basically a short amount of time at night. So if you make some assumptions, and again, this may change depending upon where you are in the country, but let's say that the longest day is 16 hours, which is going to give you the maximum backup time you're going to need, and the shortest night is 8 hours. So this is a case when you have to have your batteries recharged in 8 hours. Okay, so and that may change. I mean, it may be someplace further up north where it might be 20 hours and 4 hours. So just be aware of whatever, however long your lights are on or not on in the location you're in. And again, I'm thinking like average across the country is probably somewhere around here. So I made that assumption. Here's some examples of systems that we have done at Sunwise. Just a good example. And again, these are usually some type of Wi-Fi or radio or something like that type of thing. Okay, so I mean, you'd actually go through kind of the same process that you've done before, but a couple of other things you have to consider in this process, though, is because these batteries are being cycled daily, you want a good deep cycle battery. Okay, when you're in a UPS application, any good float battery will work fine. This is an application where you're cycling it daily. You want a good deep cycle battery. In addition to that, you're probably going to only want to discharge at 50% daily because that'll extend the life of the battery. You do not want to extend the battery to 80% every day. That's going to give you a very short life cycle. So you're going to probably want to use a 50% DOD on this one. Okay. Also, looking at this photo, this is another interesting application. A lot of these loads are small, and it's hard to get small battery chargers. So one of the other things you can do, and this is an example of one we did here, is you can actually use a power supply and with breakers and such, and run it through a solar charge controller. Now, I would refer to the charge controller manufacturer for that. Different ones allow you to do it, different ones don't. They also have different rules. Some say, yeah, you can do it, but you can only use half the rating. So if it's a 20 amp charge controller, you can't put more than 10 amps through it with a power supply or something like that. So just an interesting option. If you start working in the 5 to 10 amp range and you can't find a good battery charger there, especially with temperature compensation and everything else, to look at maybe a small power supply and then run it through a solar charge controller. Again, we do that frequently for the smaller ones, but again, you need to make certain you work within the recommendations of the manufacturers on that. So as I was saying, so let's get to just run it through. Again, it's using the same principles we've already done, just in a more advanced application here. Let's say you've got a 30-watt load at 24 volts. And again, this is going to run 24 hours a day. But we're looking at a maximum daylight of, say, 16 hours and a shortest night of 8 hours. And we're going to go ahead and take a 20% battery derate for temperature because that's a pretty common one. So if we take the 30 watts divided by 24 volts times 16 hours, we're going to get 20 amp hours at 24 volts. Okay, then we divide that by the 50% times 1.2 for the derate. We're going to get a battery capacity required of 48 amp hours. The HE22 is rated right around there at the 10-hour rate, so I went ahead and selected that one anyway. It's pretty much right on the nose going to a bigger battery certainly cannot hurt. But if you're trying to be a little more low cost, you can go down this path. The worst that'll happen is instead of cycling the 50%, it might be sometimes you might cycle the 48% instead. So keeping in mind, we took some derates up here, so maybe having a battery that is right on the nose may not be a problem. Okay, and then for the recharge rate, we've got so we take this discharge rate of the 23.8 amp hours. Okay, or you can just 20 amp hours up here, close enough. Divide that by the 5 amps in the battery charger minus 1.25, and you're going to get 6.3 hours. So you're going to recharge it just in time. So you got a little bit, you got an extra hour in there to spare. But again, this gets back to that 5 amp charger, which is going to be, in this case for us, it'd be a power supply with a solar charge controller in there. And again, we're within that 8-hour window, so we can get that done. If you're in a place where 6 hours isn't enough, you'd have to look at that a little bit more. Okay, so just a more advanced example. We're getting a lot of these late pull applications, so just a neat example of that. Okay, and again, of course, one of the other things, we have a whole tech note on this. Why should I add solar to my, or can I add solar to my UPS system? We have a whole tech note on that on our website. So again, I would refer you to our website for additional tech notes on all kinds of topics like that, as well as our other webinars we have on other topics as well, like basic standalone system sizing and other things as well. So feel free to go to our learning section on our website and review our other tech notes and webinars. And I guess we're pretty much just about out of time, but if you have any other questions, we can try to address those real quick.
We just got two one small question and one small note, Rob. Matthew had a comment that in some outdoor pole lighting circuit, there may not be enough capacity to add the additional load onto that rectifier, which is a good point, and I suppose worth noting. Rob, I don't know if you have more you want to add to that, but I suppose that's definitely a good thing to keep in mind.
That is a good point. You do need to know the other problem with a lot of these pole applications are they have higher voltages too. A lot of them are 277 volts or 480 volts that require you to either put a small transformer in or to use specialized power supplies or battery chargers for them as well. So that is a good point to think of that as a consideration, as well as the higher operating voltages they have in addition to that sometimes make it a little bit trickier. But yes, it's a good point to think about.
Yeah.
For that.
And that ties into the second question, which is about supplying 240 volts AC with the inverter/controller. And I indicated to Oscar that typically any voltage can be either consumed or supplied. We just sort of need to know about it, and then depending on how exotic it is, the solution obviously will become appropriately customizable and complex.
That's correct. Yep, exactly.
All right, well, we're a few minutes over. Give people a few more seconds if there's any last minute questions, but I do not have anything else at this moment.
Okay, well, we're waiting on that. Let's go ahead and just plug some of our next upcoming webinars. Our next one coming up later on this month is our EE102 webinar. We're going to go into more details on some of the electrical engineering principles that you can use in solar systems. I highly recommend, if you have not already seen our EE101, to definitely go back and review that one before the EE102, because we're going to build upon some of those principles and to get into more advanced stuff. If you ever wondered why when you shade a single cell in a solar module, the current goes to zero, we're going to go into the electrical engineering principles behind that. So some of the stuff you use every day, you don't understand why it does that. We're going to go into some details of why, based upon these electrical engineering theories and principles. So we're going to go into that in more detail, a little deeper in that if you're interested. After that, we have a water pumping webinar coming up. I know a lot of people have been asking about water pumping, so we're going to have a great one on that one. Errol's going to do that one. That's coming up in early February. And then later in February, we're going to do our industrial control panels. So we've got a couple more webinars coming up on that. And then in March, we got some other neat things coming up as well. We're going to try to get back into some of these hybrid systems as well as fuel cells. A lot of requests about fuel cells. We're going to start talking about those coming up in March. So if there are no other questions, thank you everybody for your time today. I hope you enjoyed the webinar. As I said before, if there are other topics you're interested in, check and see if we've already got them done on our other webinars and tech notes. If not, send us a note. We'd be happy to cover other topics for people. We're always looking for new subjects to cover that people are interested in. So please feel free to send us an email or another note, and we'd be happy to try to adjust that in either upcoming tech note or webinar. So thank you again for your time today. I hope everybody enjoyed it, and have a good rest of the day.
Thank you all.